All right, so we're in week 3, and what we should be doing is I'm just going to show the online class because those are the people who watch this video mostly. If you're in my online class, you need to do the discussion for week 3, and then everything else I'm going to say applies to everybody else, including everyone in the room here. So you have lectures to watch for week 3, and at the beginning of lectures, or week 1, week 2, week 3, at the beginning of lectures, you come in here and you can click, okay, week 1, and I'll launch it in a new tab, and this is our lecture from week 1. And then here, week 2, this is a lecture from week 2 in the fall, because I wasn't here week 2. I was out sick. So you guys had a sub. And then here is the lecture from week 3 in the fall, but after today, once this is recorded, I'll put this up here. So if you're watching this video, you've probably already found this, but tell other people who haven't found it yet. We have all the lectures there for what we do in class. So if you miss class, that's where you could always come in and find them. Additionally, just FYI, there's some good resources right here. Course outline, lesson plan. So each week, we're talking about different subjects. Week 1, week 2, week 3. And you come in here, and there's just different information. It's kind of like the main things I want you to sort of learn. And then sometimes there's links to other videos and things like that, which are interesting. So generally, that will correspond to what we're talking about. We're about a week off, which is fine, because I was gone last week. So come in here and take a look at those. And also in these lectures to watch videos, there's a bunch of extra stuff in each of those playlists, which we just never get to in class. So check it out just for your own edification. What does edification mean?
Benefit?
Yeah, pretty much. For your own education. Sometimes you have words, and the word is, just like another word, but we have 2 of them. Basically, it's education. Instruction or improvement of a person morally or intellectually. Edification. I guess there's a little bit of a difference. Instruction or improvement of a person morally or intellectually versus education. Just curious. Yeah, pretty close. Edification, education. They even sound similar. So this week, what else should you be doing? We've got assignments. So you should be through week 1, week 2, and week 3 assignments. You need to get through week 3 assignments. You have a paper, a 1-page paper to write. Just a casual, informal writing exercise just to keep you in the writing mode. Writing is like anything. How many people have a hard time thinking of what to say when you're writing? Okay. So the main intent of this exercise, casual, informal, just write like you're talking to me. So one of the best pieces of advice I ever heard or received in writing is just write like you talk. So what do you want to tell me? What did you learn the first 3 weeks? Yeah, just pretend like you're writing a letter to a friend or whatever. But, and then if it's a formal academic paper, you want to modify that slightly and not have it be quite so casual. But this is just to help you relax with writing and then also to tell me what you learned the first 3 weeks. So you need to do those assignments. And then there's extra credit. You can do that anytime. Yeah, what's up? Question?
When are the assignments on their due?
So they're all due before the end of the semester. And you should get them done by Friday, right? So you could have your weekend to relax. Like, don't be like, sweet, I don't have to do anything for 16 weeks. Because you will fail this class. It'll be just like way too much. It's like every day you need to apply yourself. It's like farming, right? You can't like not farm, all summer and all fall, and then in January be like, crap, I didn't farm at all in the summer and in the fall. I got to go farm 20 hours a day and get all my crops going. It's not going to work. All right, you kind of got to do a little bit every day, and then your crops grow well. Just keep tending them. Drop by drop, the bucket gets filled. All right, so you got some extra credit assignments in here, and you should start thinking about these. So these little videos kind of explain them. This one's pretty involved. This one's super easy. This one is pretty easy. You could just go all the way up to the place where you pay. You don't have to pay. I just want you to be aware of it because I know a lot of people, because of varying circumstances, whether it's family commitments, time commitments, financial restrictions, aren't able to pursue their bachelor's degree, you can get a bachelor's degree from an accredited university pretty much for free. It's $100 a class. And so an accredited university is what you're looking for, and it's accredited. So that piece of paper is pretty much just as good as Fresno State. It's not as good as Harvard or Berkeley, but it's probably just about as good as Fresno State. It's an accredited university for free, and you take all your classes online. So I just want people to be aware of it. I think it's so great. You show me that you went there and you're aware of it, you get a little extra credit. And that's also interesting. All right, so then in my IT lab, how many people it's helpful just to sort of see, oh, this is what I should be doing each week? You're still kind of getting familiar with the class. Raise your hand if that's helpful. Okay. How many people are a little surprised, like, at how, like, well, life is a little bit hard, right? Being born to the working class, not being born with a trust fund where you could just, like, be Paris Hilton and get drunk and throw up in bars and taxi cabs. I wonder if I could get sued for slander for just having said that. I don't know anything about Paris Hilton. I'm just going to disqualify it. She's probably not that way. Enough chit-chat. Let's talk about computers. What class are we? 454. 454. Anybody surprised? Like, whoa, it's a lot of work. Life's a lot of work. Like, I went to bed at 3 last night, get stuff done. I guess some people luck out and, like, pursue a passion and they're really good at it and then they make money at it. I like computers. All right, so week 1 was the quiz here. Week 2 and 3, so you should be down 2 assessments in here. So we're in Word now. Woo, 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 woo. Word 2010. Right? I don't care if you do the trainings. Do them if you need them. Otherwise, don't worry about it. But you need to be through this exam and through these first 2. And then down in exams, chapter quizzes through the first 3 chapters. And that's it. Okay? All right. Anybody have anything they want to share? Nothing? These will be the takeaways from today. You guys will know how computers work in about 5 minutes. That's pretty phenomenal. How many people look at this and it makes sense to you? Raise your hand. Tell me how are circuits related to coding schemes? Yeah? Let's hear it. How are circuits related to coding schemes? What's that?
I can do binary, like choose complement, stuff like that. Binary search trees and stuff.
Whoa, binary search trees.
Yeah.
That's huge.
Hard.
What language?
C++.
Sweet. You know about my Go course, right?
You went over it.
Have you started taking it? Man.
I've never taken Go. I haven't taken any like user and stuff like JavaScript and stuff like that.
Yeah.
C++, like C, Java based.
Cool.
It's fun.
Cool. So how are circuits related to coding schemes? All right, cool. I'm going to teach you something too. What about you? Cool. All right, so this is how computers work. It's just like your porch light on Halloween. If your porch light is on, it means one thing. And if it's off, it means something else. So you got one circuit, one switch, right? You could call it a switch, the light switch, or you could call it a circuit. You have one circuit, and depending upon whether it's on or off, you are storing and conveying 2 messages. If that switch, that circuit is on, come trick or treat. If that circuit, that switch is off, go away. So it's not complex. I know some of you are like giving me your thinking about it face. Is your porch light on Halloween? You know how it works. That's it. I'm done. That's the great insight. Computers are just like your porch light on Halloween. Except instead of one porch light, one circuit, there's billions of them. And you can check them instantly to see what state they're in. So there's a magnitude of complexity which is many orders greater than your porch light. But at its essence, computers are just circuits or switches that could be in an on-off state. Trip out on that. So what would it be like if we had two porch lights? How many messages could we store and how many messages could we convey if we had two porch lights? 4. What would those 4 combinations be? Pencil them out on your piece of paper. 2 porch lights. How could we convey 4 messages with 2 porch lights? Pencil out the different on-off combinations. How many people wrote that? How many people wrote something else? Cool. Now I want you to make your own coding scheme. You're going to create your own coding scheme. Okay? So for each of these combinations of circuits being in some state of on or off, have it convey a message to your Leave It to Beaver Bucky neighbor across the street so they can look out their window, see your porch light, and they'll know what message you're sending them. So create a coding scheme that when I have circuits and they're both on, it means this. When I have 2 circuits and one is on, the left is on, the right is off, it means that. So create your own coding scheme. What are you going to have it mean? Go. Anybody need a hint what I'm talking about? So if both my porch lights are on, I'm awake, come over, bring beer. That's the message I want to convey to my neighbor across the street. If both porch lights are on, the party's on. You can make your own coding scheme. So for each of those states, create a coding scheme, whatever you want it to be. All right. Share your coding scheme with your neighbor. And right before you share your coding scheme, share your name. Say, hey, I'm Todd. Here's the coding scheme. Introduce yourselves to each other. Here's the coding scheme I came up with. Go. All right, great. So you probably came up with some coding scheme. And the important thing here is that one of our takeaways is that, circuits and switches. Cool, they're something that could be in an on-off state. Second, there are coding schemes. And you just created your own coding scheme based upon circuits or switches being in some on-off state. I could have this just be, and we'll PG-ify this a little bit, come over. And this one could be go away, I'm asleep. And this one could be ah! TV, please. And this one could be walking the dogs. And people know where I'm at. Right, so that's it. Coding scheme, circuit switches and coding scheme. So imagine if, first of all, let me just say this. Instead of writing on or off, you want to do one more? Let's do one more, and then we'll do the imagine if. One more. How many messages could we convey if we had 3 porch lights? Oh, getting complicated, right? I'll give you 2 of them. You ready? There are 2 of them. And there's 6 more to figure out. There's 8 in total. And let me help you out. Instead of writing on, off, and wasting all that ink, why don't you write this instead? So for on, just write 1s. Let's have that represent on. And for off, just write 0s. Eight in total, 8 possible combinations. I hope I've been restarting this video. So the formula, sorry, were you guys done? Let me wait another minute. I'm not being sarcastic. I just started talking. The formula for how many possible combinations is 2 to the power of n. Looks like this. 2 to the power of n. So if you had 1 light, you could do 2 messages. If you had 2 lights, you could do 4 messages, represent 4 things. If you had 3 lights, you could do 8. So 2 to the power of n, where n is the number of lights or switches or circuits, whatever you want to call it, that you have. And if you have 8, you could do 256. Those numbers starting to sound like computer numbers. 2, 4, 8, 16, 32, 64, 128, 256, 512. Right? Heard those numbers in relation to computers before?
That's how our memory accelerates.
That's what?
That's how we store our memory.
Yeah. How memory grows. Yeah. So what's the next thing to learn? So the next thing we saw was that instead of writing on or off over and over and over, we could just write 1 and 0. And in computers, we say, hey, 1 means on and 0 means off. That's binary. Computers operate with binary digits. They aren't really passing 0s or 1s around. They're passing electrical impulses around. But if it's an impulse that says this is on, we just say that's 1. It's on. And if it's off, we say that's 0. Same thing. Don't get confused. Is your porch light on Halloween? Don't get that like deep thinking, this is difficult look on your face. Is your porch light on Halloween? We could do 2 porch lights. We could do 3 porch lights. We could do 5 billion porch lights. Right? And we could just start storing stuff. You hit the letter A on your keyboard. That translates to a bunch of circuits. They're not actually lights in your computer, little lights. That translates to a bunch of circuits going on or off. You hit the letter B, capital B, lower b, different circuits in a state of on or off. You can check that out. You can go to Ascii, Wikipedia. And Ascii stands for American Code Simple something. American Standard Code for Information Interchange. Leave it to people to make things more difficult than they really are. American Standard Code for Information Interchange. This is how we represent the letters of the alphabet. Coding scheme, right? I'm sure there's a simpler way they could have done it. But here's the coding scheme. And there used to be a bunch of coding schemes, right? Ascii being one of them. But if you hit the letter A on your keyboard, that combination of zeros and ones, on or off, circuits go into some state of on or off for capital A. Capital B, slightly different combination of on and off. Who knew? I am now going to hit some letter on my keyboard. Sorry, I just want you to be able to see it. I hit the letter C on my keyboard. Now, we're just speaking, learning. We're just learning right here. But somewhere on my computer, one zero 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 one one. That's how my computer got it. I got stored somewhere. Whoa. So this is the Ascii coding scheme. The world's most popular coding scheme today. Anybody know what it is? Right-click my web page and choose View Page Source. Making sure I'm recording. UTF-8. It's kind of blurry. The character set. It encodes web pages. UTF-8 is a 4-byte encoding scheme. A byte is 8 zeros and ones, 8 binary digits. UTF-8 is 4 bytes. So we just did a coding scheme with 3 zeros and ones, and we could store 8 things. Right? 3 zeros and ones, we could store 8 things, 3 circuits. UTF-8 uses 32. So if you had 1 light switch, how many things could you store? 2. If you had 2 light switches, how many things could you store? 4. If you had 3, how many could you store? 8. If you had 4, 16. If you had 7, 7. What's 2 to the power of 7? 2 times 2 times 2 times 2 times 2 times 2 times 2. 128. Who said it? Yeah, right back there. Brain power in the back. A lot of brain power in this room. You all can achieve whatever you want to achieve. Or, you know, if you work hard, you'll get farther than if you didn't work hard. Those kinds of statements like, I don't think any of you will live on Mars. I bet all my money. Odds are against it. You certainly won't live on the sun. You can't achieve anything you want to achieve. How many people have tell you've totally lost interest? How many people still are interested? And you've totally lost interest and you could just care less at this point? No? No hands? Okay. All right. So if we had 2 to the power of 32, 32 light switches, how many possible things could we store? 2 to the power of 32. We could store 4,294,967,296 different things. Well, I think that will cover pretty much every character in every alphabet in every language the whole world over. All right? So UTF-8 is a coding scheme in which we can encode every single character of every language in the entire world. So it's the current and probably always will be, who knows, the most popular coding scheme, UTF-8. So circuits and switches, coding schemes, binary. What's binary? 2. Biplane. How many wings on a biplane? 2. How many wheels on a bicycle? 2. How many partners for a bisexual? 2. Bi means 2. So binary means 2 digits. What are those 2 digits? 0 and 1. What does 0 and 1 represent? Which is which? 1 is on, 0 is off. Ponder this. What is that?
On and off.
It's on and off, because it's the on and off button. What do we have here?
A 0 and a 1.
Off, on. 0 and 1. That's a really good graphic design,
Yeah.
right? It's a nice looking symbol. It speaks to binary, and it also means on and off. It's really cool. It's a really nice symbol.
Who came up with that symbol?
I did. Yeah. And they pay me a royalty every time. I just teach here for fun. I got more money than I know what to do with. I have no idea. Somebody brilliant. So we have binary, zeros and ones. We'll also refer to these as binary digits, right? Binary digits. But then, because we're in computers and we're human, and we don't want to write things more than we have to, we'll abbreviate. I'm just looking for my abbreviation. Because I had a nice little color thing as a color slide. We'll abbreviate binary digits as bits. So we talk about bits. Or a bit, a single bit. Right, it could also just be, so plural, it could be a binary digit as a bit. So either way. But often you hear it as bits. So there's you could have a single bit. If you have 8 bits, we call that a byte. Original computers kind of worked with, at one point, computers were working with bytes, right? They're moving bytes around. So people just refer to them as a byte. Now I've just abbreviated here, and I've chopped off 24 because I like the metric quality of 1,000, 1,000, 1,000, 1,000, and it multiplies really well. To be accurate, all of those thousands would be 1,024. Why? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024. But I just said, to hell with 24 of them. I'm going to make it 1,000 because it's easier to multiply. So 8 bits is a byte. 1,000 bytes is a kilobyte, and kilo even means 1,000. Thank you. 1,000 kilobytes is a megabyte. 1,000 megabytes is a gigabyte. 1,000 gigabytes is a terabyte. 1,000 terabytes is something else, but you'll have to go look it up. Eventually, you'll get up to a yottabyte, zettabyte, and even Google, because Google is like just a big, big number. I don't know if there's a Google Byte. There's Google Bikes. Have you seen the Google Bikes? You guys seen these? They just leave them out. If you're ever near Google, you need money, just take your truck. All these bikes are sitting around. It's a joke. But they're all over the Google campus, and you can just pick up a bike and ride to some other building to work. So let's do a review. I want you to sit in your row, all four in a little group, and I want you to rehash what you've just learned with each other for 5-10 minutes. Because it's going to help it burn in. It's going to burn into your memory. So review with each other what you just learned. So did that help to do a little bit of a chat it out with your neighbors? Maybe you should have said something like this, like, okay, well, you know, computers run on electricity. Electricity can be on or off. So if we have like one circuit or one switch, like a porch light on Halloween, that can mean two things, like the porch light on Halloween, come trick or treat or go away. And if we had two lights on our porch, then that can mean like 4 things. 3 can mean 8. And so we could have these circuits in some sort of combination of on or off, and they could have a coding scheme. We could arbitrarily create a coding scheme, you know, have it mean anything. And, you know, one coding scheme is for letters of the alphabet, like Ascii or UTF-8. And so my understanding of how computers work is it's just a bunch of little circuits that are in some on-off configuration, and that configuration of on or off represents something. You know, it's like a coding scheme. And then, you know, instead of saying on-off all the time, we say 1 for on and 0 for off. And we call that a binary digit. And then instead of saying binary digit, we say bit. And if you have 8 bits, that's a byte. If you have 1,000 bytes, that's a kilobyte. If you have 1,000 kilobytes, that's a megabyte. If you have 1,000 megabytes, that's a gigabyte. If you have 1,000 gigabytes, that's a terabyte. I'm a computer genius. After one class, you guys know more about computers than the vast majority of people on the planet. You're in the top 1% right now. Seriously. Like most people have no idea. And then when you explain it to them, they're like, really? That's just like easy. Well, yeah, but the magnitude, the scale makes it complex. It's one thing to have 2 porch lights. It's another thing to have 2 billion circuits and figure out which ones are in an on-off state. And then to put it on something the size of your thumbnail, a little silicon wafer. You have a question? Cool.
Yeah. Would you consider binary to be related to like Boolean variables?
Binary related to Boolean variables? So Boolean variables, Boolean is Boolean defined denoting a system of algebraic notation used to represent logical propositions, especially in computing and electronics. A binary variable having 2 possible values called true and false. So Boolean just means that something can be true or false. It's one state or the other.
When I think of binary, I think 1 0, like 1 being true, 0 being false.
Yeah.
Instead of on and off, it's just the same.
Sure, that could be another coding scheme that on means true and 0 means false. And then I could create my own coding scheme where 0 means true. Because it's perfection, man. Haven't you studied Zen? And 1 means false. I don't know. So, sure. What else can we learn? 2 to the n, binary digits, counting binary digits, bits, bytes, kilobytes, megabytes, gigabytes, terabytes. So machine language just means that all computers really are storing as zeros, ons and offs, zeros and ones. So that's what we talk about with computers, machine language. What else would be important?
What's about 5 generations of computers?
What?
5 generations of computers.
Yeah, we didn't talk about that. So let's start here. and it is I forget the name of the movie. There we go. Did we watch this? We haven't watched it, have we? So if you're watching this video online, I'm not going to record this trailer. You got to go watch it on your own. But go watch it and come back. So it's a totally great movie. How many of you have seen it? Yeah, definitely worth checking out, right? So as you're kind of like going on a journey to learn about computers this semester, that's on my super short list of a movie about computers, and really super good movie. And it's about Alan Turing, who's you know, one of the great fathers of computer science, and really helped.
Dave kind of went over that a little bit briefly.
Oh, did he?
Yeah.
Yeah, cool. Yeah, and so there's still a Turing test, and the Alan Turing award for artificial intelligence, the Turing Award. And yeah, man, it's pretty awesome. So the generations of computers. They said that's the first computer in the movie trailer. They say it's the first computer, but if we look, first computer, and just see what comes up, we see ENIAC and UNIVAC, but the years on these are like 46, 46, and so that isn't necessarily correct. And then if you look at Bletchley Park, right, this is where the things were cracked. And let me just do this. Bletchley Park computers. See what comes up. Well, now I'm getting those deal. So here's a Colossus Computer. Was the name of a series of computers developed by British code breakers, 43 through 45. So that predates the ENIAC. And Colossus was designed by this engineer. So if we look in here for Turing, Alan Turing's use of probability is sometimes erroneously stated that Turing designed Colossus to aid. Turing's machine that helped decode Enigma was electromechanical bomb. Right, so electromechanical, so maybe not quite a computer. But you know, there's two big pushes to build computers. One was in England and one was in the United States. And I think England maybe got it with Colossus. I don't know. You might. I'm just curious. Colossus versus ENIAC. Date. I don't know. But anyhow, there's Turing's machine. He called it the bomb, or the bomb was the name of it. Though in the movie it's called Christopher. So the 5 generations of computers. The first computers had vacuum tubes. And that's what they look like. And that's what, you know, is basically a circuit which is on or off. That's first generation, so that's how we stored on-off states. Second generation had transistors. So it went from something that was the size of a light bulb and was hot down to something about the size of, I don't know, a lot smaller. Size of your pinky top of your finger. And it didn't burn out. The first generation computers were warm. I think they emitted some light, but they were definitely warm. So this gal, Grace Murray Hopper, was a computer scientist, also one of the original computer scientists in the 40s. And that's after the tyranny of time. But she worked for the Navy. She was an admiral. And she worked on these first computers. And so she would go in and debug the computers. Because the moths would fly in because it was warm, and then they'd short it out, so she'd have to go pick the moths out of the computer. Debugging the program, debugging the computer. So second generation was transistor, and that's just how we store the on-off state. Third generation was integrated circuit or chip or silicon wafer, whatever you want to call it. Integrated circuit. There's an integrated circuit. Here's a silicon wafer. Wafer, for the fabrication of integrated circuits. So, I want to see a big one. Give me a big image. That's it. That's it. Images. Search tools. Size. Large. And so these are silicon wafers. And you'll notice that there's a little grid pattern on there. Well, that's not what I want. I see different grids. So each of those is a little chip, and you cut those out. You print them all in one wafer, then you cut them out, and they would be, right? Each one would go inside of like a CPU or something, or memory. There is nothing there. Right, those are all printed on a wafer. Kind of beautiful. And that's where we're storing all the little ons and offs. How many of them get stored there? So first generation vacuum tubes, second generation transistors, third generation chips, fourth generation CPUs. How many get stored on a chip? So in 1971, 2,300. Pretty cool. And in 1980, 100,000. Whoa. 100,000 things that could be in an on-off state and could be checked. Whoa. And in 1990, 1 million. And in 2000, 10 million. And 2010, 2011, 100 million. And today, 2.6 billion more. Wow. Something the size of your pinky fingernail. There's 2.6 billion plus little circuits which can be checked in some sort of state of on or off. Wow. Quad core, quad core. Core i7, that's what's in here, I think. Core i7. So that's Moore's law and 5 generations of computers. There's Gordon Moore. Moore's law says that every 18 to 20 months, the processing power of computers doubles. And that's held true from like the 60s. That's why a computer that's 5 years old sucks. Because in 5 years, let's just say every 18 months, processing power doubles. In five years, we've gone from a computer which has the power of 1 when you buy it. In 18 months, computers have the power of 2. In 36 months, computers have the power of 4. In 54 months, right, computers have the power of 8. So in just under 54 months, which is like 5 years would be 60 months, in just under 5 years, the computers which are being released are 8 times more powerful than a computer that was built less than 5 years ago. And if you go another 18 months, so just like over 6 years, or just about 6 years, yeah, just about 6 years, computers are 16 times more powerful than what you bought 6 years ago. 16 times. And then they write software to take advantage of that extra power. So your computer wasn't built to lift to run software that requires 16 times processing power. Yours was required to do 1 processing, right? That's why your computer is like, sucks. It's too old. It's like if you were built to lift 100 pounds, and then in 6 years somebody was like, okay, now lift 1,600 pounds. You'd be like, screw that. I wasn't built for that. Or they'd give you the 1,600 pounds. You'd be like, no problem. Come back in an hour. And you'd be like, 10-pound plates. Move it one at a time, right? That's why it takes a long time. Those old computers. It's just moving things slow. Sometimes you'll hear about circuit switches, transistors, gates. Same thing. Things that can be an on-off state. Do you want me to teach you how to count in binary, or is your brain full? I don't have a pen. Oh, but luckily I created this document, so I don't have to draw anything. All right, these are numeral systems. You don't ever really think about it, use it so much. It's like the old fish saying to the 2 young fish, how's the water, boys? And the 2 young fish say, it's just fine. And then the 2 young fish keep on swimming. And one of the fish says to one of the young fish says to the other young fish, what's water? You're swimming in it, you don't even know it. You don't normally stop to think about numeral systems because you always use them. You don't think about them. But there's different numeral systems. So we use the decimal numeral system. The decimal, the prefix des is 10 in Latin or something like that. So it's base 10 numeral system. Way back in elementary school, you might have been taught that this is the ones place, this is the tens place, this is the hundreds place. And then somebody said, well, how much money do you have? I got 4 tens and I have 2 ones, so I have $42. That's the numeral system with base 10. And we get the different places by 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, dot, 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 dot. And then we just drop stuff in there. And we use 10 digits in each space, 0 through 9, 0 through 9, 0 through 9, 10 digits in each space. Because it wouldn't make sense if we tried to write 10 here, because we'd have 4. I have 4 10s and 10 ones. I have $410. No. Right? That wouldn't make sense if you just wrote 410. So that's where the analogy breaks down a little bit for that thing. So instead, if we had $410, we would say, hey, I've got $410. Oh, that makes sense. 410. What would happen if we change the base from 10 to 2? There's the 1's place. Oh, there's the 2's place. Oh, there's the 4's place, the 8's place, 16's place, 32 place, 64, 128. So I want you to give me the number, here's the number 42 in decimal. What's the number 42 in binary? Come on, you code breakers. Do Bletchley Park proud. Write it out on your piece of paper, the number 42 in binary. Use the same logic you would use for the decimal numbering system about how many in each place. Decimal, you could use 0 through 9. Binary, you could have 0 or 1. It's a binary numbering system. You only have 2 digits, 0 and 1. So how do you represent the number 42? Who needs another minute? You're still playing with it and enjoying it? Raise your hand, else I'm going to go on. Okay, 42. Well, hell, I got one $32 bill in my wallet. I got one $8 bill, that's 40. I got one $2 bill. I don't have any ones. That's 42 in binary. You would store, if you want to store the number 42 in a computer, you have this light on, this light off, that light on, that light off, that light on, that light off. Let's try another number. How would you represent the number 9? 9 in binary. This is 9 in decimal. What is 9 in binary? Nine in binary. Who got it? Raise your hand. Raise your hand, you got it. Cool. So here's 9. Give me 1 8. I can only use 0 and 1s, and I need 1 1. That's 9 in binary. Now give me 5. Give me 5 in binary. I'm giving you easy ones. Not a lot of math. 5 in binary. 1 0 1. 3 in binary. 3 in binary would be 1 1. Right? This would be 4 2 and 1. That would be 6 7. This would be 6. 4 0 1. Or 1 0 1. No, that's 5. Sorry. You guys are like, what the hell? That doesn't look like 6. That's 6. Okay, you ready for the next one? You now know how to do binary. So if you ever need to figure out binary, show it to somebody, just, well, this is the decimal numbering system, 10 to the 0, 10 to the 1, 10 to the 2. Here's the ones place, here's the tens place, here's the hundreds place. Just this same thing here. Start out with your base and just do power to the 0, power to the 1, power to the 2, power to the 3. Base 2, power to the 0, power to the 1, power to the 2. All right, now here's hexadecimal. Okay, same thing, except it's base 16. Hexa, hexa 6, is 10, hexadecimal. Base 16. We don't have 16 digits, so we use 0 through 9 and A through F. Right? So if I wanted to represent the number, what would this be? This would be 32. I have two 16s, and that's 10. That's 42. That's the number 42. 2A in hexadecimal. It's just another numeral system. It's base 16. How many people that totally you got lost on that one? You're following me up to binary, but that one just was like, eh. If you have a new numeral system, you just say, okay, what's the base? It's base 10, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, la 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 la. And I can figure out the ones place, the tens place, the hundreds place, the thousands place, right? All I got to know is the base, and I just do the power 0, power to the 1, power to the 2. For 2s, 2 to the 0, 2 to the 1, 2 to the 2. My base is 2. Now I just do power to the 0, power to the 1, power to the 2. I find out the different places. With 10, I could use 0 through 9, 10 digits. With base 2, I could use 0 and 1, 2 digits. It's base 2. With base 16, I could use 16 digits. 16 to the 0, 16 to the 1, 16 to the 2. Find my different places. Right? And then because I could use 16 digits, they have to be a single digit in each spot. So I could write them all in a line. You know, each spot only holds a single digit. I have to have 16 digits. I'll use 0 through 9 and A through F. And A represents 10. Why not? And you know what this represents? Peace. And you know what this represents? I love you. And you know what this represents? 0. You know what this represents? Loser. And you know what this represents? Thumbs up. Right, good. I like it. I like it. It's like, right? So we all the time arbitrarily assign meaning to things. We just don't ever stop and think about it. So hell with it. A's 10. Right on. And every time I do this, it means I'm glad to see you. I'm just making that one up right now. So when you see me walking on campus, and I'm like, you can do it back, and people are like, what are you guys doing? You're like, that means I'm glad to see you. You don't know that? Those are numeral systems. Talk to somebody, your homework for tonight. Tell somebody at home or a friend everything you just learned in here. Like within the next hour or two if you can. Like just go like your girlfriend or your boyfriend or whatever, your dog, and then it's on or off, and your dog will be like, he's talking to me, it's good. See you guys Wednesday.